let's talk more about algebraic methods now that we've covered the limit laws. One of the easiest and most straightforward ways to evaluate a limit is using direct substitution property. Basically, what the direct substitution property says is that if you pick a number, call it a, right? We're taking x to a, and it happens to be in the domain of our function, you can simply just plug it into your function, right? As some regular input that you're used to working with, and you get some output, and that will be what your limit is equal to. But you have to just be very careful. A has to be in the domain for this to work. If it's not in the domain, then we may have to try something different. So let's look at these two functions down here. Not all functions have this property. This is this concept of continuity, something we'll explore more later on. So a couple of things that I like to do when I am going through them and I'm evaluating limits and I'm just trying to be efficient with my time is I just kind of look at the function and I make a note of what kind of function it is, and then that'll tell me a little something about the domain, right? So this one is a polynomial, and the domain of polynomials is all real numbers from negative infinity to positive infinity. That just means you can plug anything into it, right? And so since we are taking the limit as x goes to 5, everywhere I see an x, I'm going to plug in 5. And this is where that, like, I can add and subtract the limits and I can multiply by a constant come into play. But it's nothing different than what you've been working with in the past, right? Where we just get to simply plug x equal to 5 in. As long as we get an answer out, for example, this one we get 39, we say the limit exists and it equals 39. Now, you may not always memorize the domains of all these functions, and that's okay, right? So like for this one, this is a rational function. For a rational function, you do have to be careful of division by 0, right? And so the only place where this particular function equals 0 is right here where we set the denominator equal to 0, right? So we get 5 equal to 3x, divide both sides by 3, and we get 5/3, right? And so what we notice, though, the thing that we're taking the limit to is not 5/3. So when we are evaluating this limit, I can simply plug -2 in, so -2 to the third plus -2 squared minus 1 all over 5 minus 3 times -2. Do a little bit of calculation and we get -1 over 11. Right? If you don't remember this like domains and this division by 0, the only thing that you just have to look out for is just like things that fall apart. Right? So like for example with these rational functions, I'm going to write it right here because we're going to explore this topic down here. If I take the limit as x goes to some number, as long as it's not positive or negative infinity, right, of some function, let's say it's a rational, right? And you do the direct substitution and you get something that looks like this, 2 divided by 0, right? All this tells you, it doesn't tell you D and E, right? We keep talking about that. I'm going to keep stressing it. All this tells you is that that number itself is not in the domain. Direct substitution won't work here. So won't work here. This means try something different. Either one of these approaches we're going to talk about in a minute, or one of the other previous approaches where you either look at the graph or you look at the table, which seems to be the most common go-to, right? Assuming that certain things, right? So we did learn a tactic where we divided by the lowest or the highest power of the denominator here, with functions that look like this, I want you to be very careful with that tactic. You cannot do that here. So, right, you can't divide by highest power of denominator. Let's talk about why. That tactic was only good for when the limit went to positive or negative infinity. Right? So I'm going to say because x is not going to, let's actually write it out, not going to plus or minus infinity. It was only these ones, for example, where we were able to kind of utilize that tactic. So be very careful with that. All right. So let's talk about, when does direct substitution not work, right? If it works, do it, go for it, try it first. That's always my go-to. Nothing wrong with that. But what if we end up in this case, for example, where we have division by 0 like we wrote in pink? So let's read through these cases really quick. What happens in direct substitution if A is not in the domain? Here's an example, right? Leads to denominator being 0, for example. So the answer is there is a factor of 0 in the denominator when evaluated at that point A. Two cases, though, when that happens. The factor, let's kind of highlight the main parts of this. The factor shows up in the denominator and it can be canceled with the same factor in the numerator. So we'll talk, that's one of the easiest cases. We'll talk that one first. So that's case 1, right? Where let's say you have a function, for example, let's say x squared minus 1 over x minus 1. This particular function can be factored in the top and the bottom. And these x minus 1s, assuming we're taking the limit towards like 1, where the domain doesn't exist, we can cancel it and get a new function out, right? So that's case 1. Case 2 is basically it doesn't cancel, right? So case 2, it's already in simplest form. And so therefore, for example, you get like something like this, like 1 over x minus 2. This is already simplified. You can't cancel it. You can't make it look a little nicer. You can't pull things out of the denominator. I'm just going to go ahead and tell you right now, this is where we're going to need our other methods, right? So you need the graph or numeric method. So our goal right now is to work on the algebraic method. And so the first fact that we're going to use is this mathematical fact at the bottom. And so what it is saying, so right here down at the bottom, what it's saying is if two functions, let's say here is f of x. I'm going to try and make them, let's make it easy on myself. Let's make them lines. Let's say here is f of x. Here is another function, call it g of x. What this is saying is that these two functions are equal. Their outputs are equal except for maybe one x value is what that means. So maybe we get a nice linear graph that looks the exact same except at one value. Maybe there's a hole in the graph, right? Something is a little different about these graphs. Everything is the same except for this point right here. This point is there, it's done. This point's not included, right? What this definition says is that if the limit as x goes to a of f of x is equal to the limit as x goes to g of x as x goes to a, they are the same provided that the limit exists. Remember, the limit doesn't care about the hole, right? And so what we notice is that the right-hand limit and the left-hand limit are going to the same value, therefore the limit exists. This one, limit definitely exists. Everything's defined, everything's in the domain, right? These means that they have the same limit at that particular value right here. And we can kind of visualize that with the graph. right? So algebraically, go ahead and jump to the next page. What we notice, we have a rational function. We can look out for the division by 0, or you can simply just plug it in and notice that you will in fact get division by 0 here, assuming that you plug your 5 in for x, right? So this just tells us 5 is not in the domain. But we cannot conclude D and E, right? What this tells us direct substitution doesn't work. Substitution doesn't work. This is not D and E. Don't jump to that conclusion. Do something else, right? And so what case 1 was telling us was check and see if it can be simplified first. Let's write that. Check if the function can be simplified first. The goal is efficiency here. Yeah, we could look at the graph, but we don't always have the graphing calculator, especially on a test. We've got to learn other tactics. Sometimes the graphing calculator doesn't graph functions well either. We could use the table, but it's time consuming, right? And the goal is to be a little bit more efficient. This is going to definitely be faster. So, plus you'd have to check the limit as x goes to 5 from the left, checks the limit as x goes to 5 from the right. Just a lot of unnecessary steps unless you really have to, right? So x squared plus x minus 30 all over x minus 5. This is where our factoring comes in. This top portion can be factored to x minus 5, x plus 6 over x minus 5. I have a factor on the top that can be canceled with the factor on the bottom. Therefore, I can rewrite this function to look like x plus 6. Now 5 is in the domain. Basically, I can plug it in now and I can get an answer. That's all that means, right? Plug it in, see what happens. 5 plus 6, you get 11, you're done. What this also, right? So this example is a prime example of this picture that I showed you on the previous page, where this function looks like this line, except it's gonna have a hole in it, right? And so basically the functions are the same except for one spot. So let's write it really quick. Maybe down off to the side. X squared plus x minus 30 over x minus 5 is equal to x plus 6, except at x equals 5. Which means if you can find the limit of this, like we did here, then it will be the same limit as your original function. And actually what you found is the location of the hole. We found the hole in the graph, where the x value comes from the limit, and the y value of that hole comes from once you plug it in and you get the output for that limit, right? And so essentially what the graph of x squared plus x minus 30 over x minus 5 looks like, it looks just like the graph of x plus 6, right? So a y-intercept of 6, a slope of 1. See if I can draw this graph okay. Sure, that's one way. Let's get the other way going. And then what you found, but it's going to have a hole in the graph right here. Okay, so there you go, right there. So everything else is the same, except there's like a little blank part right there. But we use these circles to represent holes in the graph to make it very clear to our reader. Let's try one more. Again, right? If you don't recognize that things are in the domain, it makes it a lot faster if you do notice kind of just straight away that x equal to 2 is not in the domain. In the last example, I put together the graph for you so that way you had kind of the visual that the left-hand limit and the right-hand limit did in fact go to 11, which meant that the big limit for this also was 11, but we didn't actually use the graph to show it, right? It's just there for you to kind of confirm. So for the second one, we're just going to use the tactic no graph needed. So we want the limit as x goes to 2 of x squared minus 4 over x minus 2. This is a difference of squares formula, right? So x squared minus 4 can be rewritten as x squared minus 2 squared. And we have a formula that says if we have something squared minus another thing squared, we can rewrite it as a minus b, or first thing minus second thing, a plus b. So x minus 2, x plus 2. You just got to recognize what value is being used. Not 4, 2 here, right? So x minus 2, x plus 2 over x minus 2. Once you have those like factors, you can cancel. So I have the limit as x goes to 2 of x plus 2. And even if you're not sure if you can plug it in, try it. Worst you do is take a couple extra minutes. You get a number out, you're all set.